Hello, my dear students, and welcome back to my kitchen and the door to my laundry room. I want to finish exercise 4.4. So, this is exercise 4.4, part 2, where we're continuing to finish this chapter on reactions and aqueous solutions. But those are solutions. Solutions are mixtures of a solute and a solvent to make a solution. A solute dissolved in a solvent, dissolved, lots of sols, and I'm giving you the solutions to these solution problems for questions 9 through 13. If you haven't, you need to go back to the first part and watch the first 8 being done. So in the first 8, what we did was we gave you a molarity and asked you to work back to tell me how many grams are in 1 liter of that. Of course, it doesn't have to be a liter. How many grams in half a liter? You just divide your answer by 2. How many grams in 2 liters? You would multiply it by 2. Well, this works backwards, gives you your mass, and doesn't give it to you in 1 liter. So you have to do another extra conversion. The first one says 8.7 grams of calcium bromide in 250 milliliters of solution. Calcium's a group 2 metal. I've got my pencil and not my marker, but it always has a 2 plus charge, and bromine is a group 7 halogen. It always has a -1 charge. If you add up 2 bromines at 79.904 and 1 calcium, a fairly light metal, 40, it's period 3, 40.078, then you get 199.886 grams per mole. Okay, I'd be fine if you went with 40 and 80 and 80 and just used 200 there as well. Because you'll see we really only have 2 significant figures. Does it say 8.7 or 8.70? 8.7. So, I should have put a 0 there probably. 8.7 grams in 250 moles. The way I was taught to do it, some of you may have been taught in high school, draw these long lines and do your factoring that way, but I just picked the first one. I want this answer in moles per liter, so I need to get rid of the grams. The thing that gets rid of grams is my molar mass. Instead of doing 109.936 grams per mole, per 1 mole like we did in the last one, we have 1 over 1. That is called an equivalency. Each of those is equal to the other. I flip it. Instead of 199.886 grams per 1 mole, I write it as 1 mole per 199.886 grams. And now my grams cancel and I'm left with moles in the numerator, which is what I want in the end because it asks what is the molar concentration. Moles per liter. Molar concentration is measured in moles per liter. So this, however, was in 250 mils. There's 1,000 milliliters in 1 liter. So I can put another conversion factor in there and cancel out my milliliters. But if I multiply 8.7 times 1,000 and divide it by 250 and then divide it again by 199.886, I get 0.174 moles per liter. And it really should be just 0.17 moles per liter because we only have 2 significant figures. Okay, so we worked it backwards. Once again, you have to step aside and calculate your molar mass of your compound or look it up. In the lab, what do? I grab it. I'll show you next time. I didn't think to get a bottle handy, but I just look at the bottle, written on the side of the bottle before I go to the balance to weigh it out. It gives me my molar mass. The next one is lithium sulfate. Lithium is a group 1 metal. So it's always +1, so I need 2 of those. And sulfate is always SO4 2 minus. I have 1 sulfur, 4 oxygens, 2 lithiums. It adds up to 109.936 grams per mole. I simplified my task this time because even though they said I put 9.8 grams of lithium sulfate in 300 milliliters, I know if I take a 1 liter graduated cylinder, that I'm only going to measure out 300 milliliters or 0.3 liters. I just did the conversion in my head. 300 milliliters is 0.3 liters. If you want, you can do this. 300 milliliters times 1 liter per 1,000 milliliters. Okay? Milliliters cancel. I end up with 300 times 1 over 1,000. I don't know how you do your division, but that's 3/10 or 0.3 to me. So 0.3, I do have 3 significant figures, 0 liters, and all I did was simplify it and do my conversion to liters, which I must do because our molar concentration is in moles per liter. So I have 9.8 grams per 0.3 liters, and I know that 1 mole from my previous calculations is 109.936 grams, and that gives me 0.2971 moles per liter, but I can only have 2 sig figs, and that rounds to 0.30, correctly rounds or properly is reported as 0.30 moles per liter, which is the same as 0.30 molar, big M. Watch your units. The next one has 12.4 grams of sucrose. That's cane sugar or table sugar. The sugar we eat way too much of. In 750 mils or 0.750 liters. Its formula, it's made up of a glucose hooked to a fructose. Its formula with the with the dehydration synthesis reaction, so that we have 1 less water. It would normally be C12, the two together, glucose and fructose, would be C12H24O12, because each one of them is C6H12O6, but we remove 1 water, so it's C12H22O11. So 12 carbons times 12.011, 22 hydrogens times 1.008, 11 oxygens times 15.999 gives me 342.297 grams per mole. It doesn't look exactly right. Maybe I should have looked that one up. But assuming that is correct, 12.4 grams in 0.750 liters multiplied by 1 mole per 342.297 grams. Grams cancel. And I'm left with moles per liter, which is big M molar. And I have 3 significant figures. It's 0.0483 molar. Yes, that's what I got, if I copied it correctly. 2 more. One quick one, one longer one. 14.2 grams of iron nitrate hexahydrate. We haven't really covered hydrates. I usually cover this as a laboratory exercise where I have my students heat up a hydrated salt, drive the water off, make the anhydrous salt without water, and calculate the molar ratio of water that was driven off. Knowing the molecular mass of this and the molar mass of water, which is 18, those calculations are relatively simple. But many compounds are typically found as hydrates. Water, not covalently, but tightly bonded to it in a regular ratio. And this one is 6 waters for every iron nitrate. Nitrate's -1. This iron 3 is iron +3, so I need 3 nitrates. And I also need 6 waters to include in my molar mass when I weigh it out. Often these hydrates behave better, are more crystalline, are easier to work with, aren't as clumpy. Sometimes they are more clumpy, but you know, they are the preferred common form. And even if you buy the anhydrous salt here in Arkansas, with the humidity that we face, my anhydrous salts quickly turn to the hydrated form anyway. Unless you really are careful about tightening the cap, maybe wrapping it in parafilm, maybe storing it in a desiccator, it's too much trouble. Okay? A vacuum desiccator or a desiccator with some dryer right silica gel in it, you know, all that gets more expensive, more time consuming. We just work with the hydrate. And it's very common. And we write that with a large dot and the molar number of waters per molecule of this compound, or per formula unit of this compound, because we're typically talking about salts. Anyway, 1 iron, 3 nitrogens, 9 oxygens plus 6 in the water, or 15 oxygens, and 12, 6 times 2 hydrogens, adds up to a molar mass of 349.947 grams per mole. The only trick is you have to include this water in your formula mass determination. This 14.2 grams in 0.300 liters, knowing that 1 mole is 349.947 grams, gives me a molarity, or a concentration of 0.135 molar. Okay? Now, what if I take this solution and dilute it 1 to 10? Or you just move the decimal point over. It'd be 0.0135 molar. But what if I don't do it quite so straightforwardly? And that's what the last question asks, which I've written actually over here. And a famous equation that I learned is V1N2 equals V2N2. Luckily, we don't work with normalities very much. It's the same pretty much as molarity, except you're doing it in grams of water instead of mils of water. That makes a difference in temperature. It makes a difference in things that have varying specific volumes, to where we're changing the volume significantly or beyond the precision and accuracy we're trying to work with, because they have a partial specific molar volume of such and such that they change volumes. And so this, some people in the old days like to use it a lot more than we do now. But normality and molarity are pretty much the same for us if we're working at 4 degrees, I guess, you know, where, is it 4 degrees, where the mass of water is, that's its densest point, but where we assume 1 milliliter of water equals 1 gram. And for our practical purposes, that happens everywhere in the temperature range we're working and at the level of precision we're working. You could put an M here. As a biochemist, you'll see the biochemists do it this way. Concentration of solution 1 times the volume of solution 1 is equal to the concentration of solution 2 times the volume of solution 2. But this is the equation you use for dilutions. And they said a 10 mil sample, actually a 10.00 milliliter, ml sample, 10.00 milliliter of a 1.07 molar solution, 10.00 milliliters, of a 1.07 big M molar solution, that means moles per liter, of potassium hydrogen phthalate. You're a good chemist if you can spell phthalate. It's pronounced phthalate. The pH is silent. But the phthalate, they gave you its formula mass, so they're not even asking you to add it up. It's a moderately complex organic molecule. And this, you may have heard of phthalate esters. Those are things that you don't want in your water bottle because they have perhaps estrogenic or perhaps carcinogenic properties. But anyway, these phthalates, this potassium hydrogen phthalate, is diluted to 250 milliliters. Now, if your two volumes are the same units, the units will cancel. You don't have to convert that to liters, even though our concentration is in moles per liter. I'll show you why. Volume of 1 times the concentration, normality, or molarity of 1. So 10 milliliters of 1.07 molar corresponds to equals 250 milliliters of some new molarity. So we solve for X. We just divide both sides by 250. So I have 10 milliliters over 250 milliliters. The milliliters cancel. And if I multiply 10.107 and divide by 250, I find that my X is equal to 0.0428 moles per liter. I have 4 significant figures here. I have 3 here. I have 3 here. So I figured I could use 3 here. So that's the first question. What's the molarity of the final solution? When I dilute it out, I just fill in my equation. They give me how much of the original solution I had and its concentration, and they told me how much I end up with in the final solution, and they want to know its concentration. Or you can work backwards. So that's the first part. Then the next one is just like the other ones we just did in the previous video. They give you a molarity and they say, how many grams are there? Well, here's our molarity, 0.0428 moles per liter. And I have 250 or 0.25, I should only have 1 0 there. Nope, it's 250.0, so I can have 4 zeros. I forgot my 0.0 there. So 4 sig figs there, actually. So they allow you. I could have gone out a little further, I guess. 1 decimal further, 1 place further, not 1 decimal. That's kind of slang. 1 place further, or to my 5th decimal place, or to my tenths, hundredths, thousands, 10,000s, to my 100,000th place, to be precise. With apologies to my math teachers, but the point of this is how many grams of potassium hydrogen phthalate are in that 250 mils? Well, I know its concentration is this many moles per liter. I know its molar mass, so I can convert those moles to grams. I know how many liters I have, 1/4 of a liter. The liters cancel too. And in the end, it'll tell me how many grams I have. Do the math. I did it on my calculator. And I got 2.185 grams of potassium hydrogen phthalate. And luckily they gave us the abbreviation KHP because I hate writing out potassium hydrogen phthalate or phthalate ester or phthalic acid or any phthalates because I lived in Germany for 2 years, but I don't spell those German words very well. So, in my day, if you were going to be a chemist, the language you had to take was German because many of the early organic chemists were German. If you were going to be a microbiologist, you took French because of Louis Pasteur. If you were going to be, a chemist, it was Emil Fischer and his especially an organic chemist, his students and contributions that many of the original papers were written in German. And we still see that all the time. W for tungsten in the periodic table. W is the first letter of the German word for tungsten, Wolfram. And we still use K for constants and equilibrium constants and the like, because the Germans spell constant with a K. So you see this German history all the time. My UPS driver's here, so I will say goodbye now. Stay safe, and I will see you in the next video. I have some videos for the next couple chapters I will post before spring break, but they won't be due until a week after spring break. Goodbye now.